Okay, so this is a challenging question, but a good one, I think. So, there is a proposal to provide a quicker, more efficient, and more environmentally friendly system of inner-city public transport by using electric taxis. The proposal necessitates the installation of power sources at various locations, as the taxis can only be driven for a limited time before requiring recharging. The graph shows the speed v in meters a second that the taxi will maintain if it is driven in such a way that it uses all its energy up in t seconds. The curve is a section of a parabola which touches the t-axis at t equals 0. Also, when it touches the t-axis at t equals 900, and when t equals 0, v equals 25. Okay, you might have noticed I crossed something out there. In order to fully understand this question, it's important to understand what's going on. And I think that term constant speed confuses things. I could be wrong, but what I think is happening is you're attempting to drive your, electric taxi at a constant speed, but as you drive, your electrical energy in the battery decreases until at some stage you come to a stop. That's how I've interpreted this graph. So, you're trying to drive it at 25 meters a second, but as time passes, after 900 seconds, yeah, your electric taxi is going to come to a stop, which is represented by this point here. So I think the fact that it says it's driven at a constant speed is confusing. But then again, I could just be interpreting it wrong. Anyway, it doesn't really matter in terms of interpreting the question. So let's have a look at the first part. It says construct a rule for V in terms of T. So part A, okay, it says it's per section of a parabola, and we know that parabolas have this rule, y equals A times x minus h squared plus k. Okay, but we know in this case that along the y-axis, we have V. So we've got V equals A times, all right, x is now T because that's on the x-axis, minus h squared plus k. So it's taking this form. But we also know that this point here must be the turning point. This must be at 900, 0. So what we have is we have v equals a times t minus 900, because it's been shifted 900 units to the right. And, it hasn't been moved up or down at all. So we know that k is 0. So if we come over here and finish things off, we can say that we can find A as well, because if we want to find A, we can just sub in this coordinate here. We know that this coordinate is at 0, 25. So if we sub that in, we know that when V is 25, we don't know what A is. That's what we're trying to find. We know that T is 0 though. Okay, so we get 25 equals 810,000 multiplied by A. I've done this a lot of times now. So I know that negative 900 squared is 810,000, but you have a calculator, so you can do that. And then we can get A equals 25 on 810,000. And that simplifies to 1 over 342,000, I think. Let me just double check that. 25, let's have a look. 25 over 810, 1, 2, 3. We want it as a decimal. We don't want it as that. Yep. 324,000. Lucky I checked that. 32400. Oh, these need a swap. 32400. Okay, so we know now that the rule for V, now that we know what A is 1 over 32400 multiplied by T minus 900 squared. Okay, that's the first part. Construct a rule for V in terms of T. Okay, if S meters is the distance that a taxi can travel before running out of electrical energy, write down a rule connecting S and T. Okay, this is where it gets a bit confusing. So for part B, we need to think a little bit about physics, very tiny bit. We know that in physics, speed, which they've called V in this case, is equal to distance, which they've called S, over T. So that can be a bit confusing. V, just recall, is speed in this case, and S is distance. Okay, if we rearrange this for S, which is what we need to find, we need to find a rule for S in terms of T. We know that S is equal to V times T. Okay. And V is all of this business. So what we're going to get is S equals V. Okay, times t. So I'm going to take this v thing and multiply by t. That's just going to put t in the numerator. So t over 32400 multiplied by t minus 900 squared. And that is your rule for the maximum distance that the taxi can travel. So we can tick off part B. Part C says use your CAS to help draw this. So what we're going to do is we're going to get our CAS up and we're going to go to a main page. We're going to go to menu, graph and table. Okay, we're going to graph this and we're going to go keyboard. All right, we can't use T on the calculator. We have to use X. 32400 multiplied by X minus 900 squared. If we tick that and then graph it, we're going to get something like this. And it doesn't look like it's fully graphed it, but we just need to adjust our settings. So this is up to you to have a bit of a play around. Time can't be negative, so the minimum time can be is that. So let's maybe make it, just go larger than you think. So maybe go to 1,000. And again, this is up to you to sort of play around. Y can't be negative, so let's go up to 2,000. Yeah, it's not too bad. If we just zoom out from there, we get a bit of a clearer picture of what's going on there. So that's not too bad. So we have this sort of cubic situation going on. Notice that obviously the taxis can't run forever. So the maximum distance, this part of the graph is irrelevant. We actually don't really care about this part. We only care up to and include up to that, up to and including that point, that first x-intercept. Or rather, should I say the second x-intercept, this intercept here. Okay, so that's the graph. I suspect that you can analyze that. So if you wanted to, find the maximum point there, you can do the analysis as you need, and then you can graph it. So let's tick that off. We've used our CAS to help draw the graph. Okay, it says originally the power sources were to be located at 2-kilometer intervals. However, there is a further proposal to place them at 3.5-kilometer intervals. Is this new distance feasible? Okay, let's go back to the CAS and let's have a think. What we can say is that we know along the y-axis we've got distance, which was our variable s, and that's measured in meters. So 2,000 meters, you'll notice, is comfortably within the maximum range of the taxis. Remember, this blue line represents the maximum distance that the taxis can travel. And so that's below the maximum, so that's fine. What might be interesting is if we do 3.5 kilometers, which is 3,500 meters, and then we graph that, you notice that that line is actually above the maximum range of the taxi. We saw before that the maximum range of the taxi was about 3.3 kilometers. So 3.5 kilometers is outside the range. So having the charging stations 3.5 kilometers apart is actually not feasible, for this city planning or whatever they're trying to do. So we can't have that. Okay, so that's our reasoning for that part. Okay, the last part is a bit tricky. So with the power sources at 2 kilometers intervals, use your graph to determine approximately both the maximum and minimum speeds recommended for drivers. Explain your answer. This is where I'm going to go to Desmos and we're going to have a look here. So this is the graph. And as we said, we're only interested up to this point. And then this is where, the taxis have traveled 2 kilometers, 2,000 meters. Okay, just, let's think about how electric taxis work for a second. You can travel at a slower speed for longer, or you can travel at a higher speed for shorter. So let's see if we can make some sense of it. These points here, and let's get our calculator back up. These points here. This first point at 101.675 2000 is saying that you can travel 2 kilometers in 101.675 seconds, which must mean that you're traveling at a speed of, and we just got to work that out, 2000 divided by 101.675. If we press enter and press decimal, okay. So what that means is we can travel at 19.67 meters a second for 101.675 seconds, and that would be our maximum speed that we can travel 2 kilometers at. Okay, this one over here is going to be 2000 divided by 559.759. Okay, if we press enter, Okay, so we could also travel the 2 kilometers at a speed of 3.57 meters per second. Yeah, so we can travel slower for longer amount of time, or we can travel quicker for a shorter amount of time before the battery runs out. So there are your two answers. The maximum speed you can travel at is 19.67 meters a second, and the minimum speed you can travel at is 3.57 um, yeah, meters per second. Hopefully that clarifies that question. It's a bit of a tricky one, but hopefully making a bit more sense now.